2 minutes? Okay. So by the time everybody is settled, then let's start. And we proceed with the topic that we started yesterday. And the topic is maybe not the most easiest one. It's about the dynamics, modeling of robots. And yesterday we looked into kinematic chain, different kinematic chain. And what we looked at was what we call stationary kinematic chain, like a robotic arm, like a robotic manipulator that is founded, based on a foundation, that means base fixed, right? And now we are going, so maybe just ask, did you have questions? Because yesterday I know it was a lot, maybe you didn't have the slides, did you? You're going to get them. Anyway, do you have questions from yesterday still remaining? If not, then let's proceed. And today we're going to kind of extend this approach to floating kinematic chain. Okay, floating kinematic chain in the sense that so they call it also floating-based systems. Okay, floating-based systems in a sense that you have now not only the, for example, like this robotic arm, but you have it on a mobile base. And the mobile base, because the mobile base is mobile, that means not fixed, not stationarily fixed on the ground, they call it floating base, because it could be anything, right? Because so this is modeled in the different ways of modeling this. For example, you know these things, these omni wheels. You might have like standard wheels, like castor wheels, like follower wheels. You might have a UAV. Right? Some of you working on UAV, some of you work on underwater things, and whatever. So this base might, exhibit certain motions. It might be allowed to have certain motions. So in the modeling approach is that you model it first as a free floating system. That's why it has the name free floating system. What did I say? Yeah, free floating system. A floating base system. Floating-based systems, and then you introduce the interaction of the base with the environment. That could be, for example, due to the rolling position of standard wheels, or this kind of mechanism wheels, or omnidirectional wheels as they call it, or it might be due to the interaction with the fluid. You might have fluid structure interaction. This fluid structure interaction is something that is not easy to do, as some of you have already realized. This is not our topic. Our topic is just, in quote unquote, just to model this floating-based system in the sense that we have this big rigid body, the base, on which is mounted a kinematic chain. And of course, I like to repeat this this example, this robotic hand, because you can model a robotic hand or any kind of part of a system as a floating-based system, in a sense that you first model the hand, for example, or whatever model, whatever system you have, and then you say, okay, this base, later on maybe, is, fixed something. So once you have the equations for the system with the base free floating, you can then later on say, okay, the base is moving according to whatever, right? And there's a topic that's called subsystem modeling, and in particular, this is one way, this is going into the direction of subsystem modeling, because you can say that, for example, this is a subsystem of the big system, okay? And yeah, this is a different topic that is beyond our lecture, but you may already think or see that this is possible to do. Okay, so how do we do it? Essentially, we can just follow up on what we did yesterday. We can hopefully use the equations, the dynamic motion equations, as they call them, of the kinematic chain that is, which is now moving. The base is now moving according to some other means, right? Some other means. Okay. What we did in the past was we said we have one, and that's what we're going to do again. We have one space fixed frame, and that's called the inertia frame. Okay, so the space fixed frame is still there. But now the robotic arm is not fixed relative to this space fixed frame, but what it's doing, first of all, how do we model it? The frame that was fixed originally to the space, fixed ground, is now, again, of course, fixed to the first link. I mean, that's still called 0 link of the robotic arm, but now it's not itself relatively to the space fixed frame stationary, but it's allowed to move. Okay, so this is essentially it. So just long story short, in the past, I mean, yesterday what we did, we said this frame is actually the space fixed frame, the inertial frame, and now what we are now saying, there is a separate frame which we are using to describe the motion of the kinematic chain, and this one is allowed to move relative to the space fixed frame. Okay, so that's the basic concept. And of course, now what we have to do, we have to look at the kinematics first, right? So how do we model the motion of the kinematic chain, and then, the motion of the kinematic chain, and then of course the dynamics. Okay, we have one more object. Apparently, we have the base, right? This whatever it is. I mean, it might just be a very complicated system, or it might just be a rigid body. Let's say we have the base represented as a rigid body. That means we have, as I was saying, the base frame, and the base frame is now somehow moving relative to the inertial frame, and of course we use a homogeneous transformation matrix to describe the motion. This means the pose of the base relative to the inertial frame. Okay, and this is then this H0B again, right? And this H0B, of course, is time dependent. Okay, right. Good. So this is the setting. What do we do with the end effector motion, for example? Or what do we do with the motion, I mean the configuration, the pose of body I in the chain? So we have, again, I mean, we still have the same kinematic chain, for example. We have 1, 2, 3, 4, in this case 6 bodies. And those bodies are now, I mean, of course, moving relative to the space fixed frame. But we do this detour via the base. And the base is here. And so we just have to take into account this the space motion. Okay, so again, what we do is to use this product of exponential formula, in the sense that the motion of each of the bodies relative to the base frame, which was for a stationary system the inertial frame. So relative to the base frame, we have again this standard form. I mean the one that we introduced already. Okay, that's nice. But this gives you the motion of body I relative to this frame. So what we have to add, so to say, is the motion of the base frame relative to the inertial frame. So the base, whatever it is, the thing is moving, and this is encoded into H0B. And H0B is just a function of time. Somehow it's moving. Okay, yeah, that's it. So and what we have now is the, again, H0I, and I skipped the 0, so we have the HI that gives you the transformation from each of the body frames to the inertial frame. Only by using the detour via the space frame. Okay? And there we go. Now the overall system configuration is described by the joint angles, as well as that pose, I mean this homogeneous transformation that transforms the base motion, the base frame to the inertial frame. Yes. By the way, what we did yesterday, we said we have these motion equations, just maybe to introduce a term, because what we said yesterday is that we had our motion equations in terms of, for example, yesterday we said Q, right? So this is a vector, and this is normally so we have n components, and that's just for simplicity's sake, they come from Rn. And this is normally called the generalized coordinates, or the configuration of the system, right? So this is actually encoding the configuration of our system, simply because once you specify Q, the system pose, the configuration is uniquely determined. And now we do a bit of an extra thing, because now our Q is the joint angles vector plus, I mean, including this, or the other way around, is this H0B, and of course the theta. So, and that's again our configuration, right? So this is the same, saying this is the configuration of our system. Why I'm saying this is now, this Rn normally gets the name because it's the configuration space, right? these Q's, they are normally called the minimal coordinates or generalized coordinates, right? So, or generalized coordinates, it's a different term. I mean, if you look into the Lagrangian mechanics, then you find all this term of generalized coordinates. Yes, so anyway, so, and the Rn in this case, in the first case, is the configuration space, right? Because the vectors Q, they're representing the configuration, right? Each of the Q's, or let's say the theta, depends which system you're having, uniquely specifies the configuration of the system, and all of these Q's together make a space, and this is the configuration space. Okay, it's an n-dimensional space, and yeah, and that's it. Yeah, just for completeness, because that is something important which we didn't say yesterday. Okay. Now we have a different configuration space, of course, because now we have one more element, which is this homogeneous matrix. And we have been saying that these homogeneous matrices, again, they form a space, and we even said that they form what we call a Lie group, and we call this SE3, right? So essentially, our configuration is the original one, like theta, just the joint angles, and that could be like Rn, but I use Vn, times SE3. Yeah. Okay, maybe I should, because I had one little detail that you might be interested in, which is the question about this configuration space. I was saying it's Rn, right? So let's say you have these. So let's say we have these joint angles, and let's call that theta now. Q, theta doesn't really make a difference. Let's call that theta. Okay. So we have theta 1 up to theta n. Okay. And let's say that these are. So these are the joint angles, right? So we have like n orbital joints, like in this, typical example of this robotic arm. So what's the space actually that this guy is living in? So this is an n vector. What would you say? Huh?
Then it would be n-dimensional space.
So is it like Rn or something? Is it okay? Like this? Yeah, like Rn. Are you sure? The funny thing with these level joints is okay. Let's say we look at one joint. So let's say this is 0, right? So this is like theta 1 or whatever. Okay. Now, so you start turning, right? You start rotating, and then you reach pi, for example. Okay, and you go the other way, maybe you reach minus pi. So what happens if you go further?
2 pi.
Yeah, I know that you might. But physically, what does it mean? You're coming back to the same point, right? You're coming back to the. So it's all modulo 2p, right? 2 pi. So and topologically, what they say is that actually because you have to somehow identify. Let's say you are here. You are for example here, right? Let's say you have now 3/2 pi, right? Which is the same like saying. What is it the same? It's the same like saying I'm here in minus p/2, right? So in this sense, you can actually identify the two ends here, because once you're going in this way, you're actually coming this way, right? So you can actually kind of close the loop here. So and this is why topologically, the configuration space of a level joint is not Rn, but it is the circle, right? So essentially, it's a circle. It might sound a bit of far-fetched and a bit too esoteric, but if you do motion planning, for example, that's important. If you have your A-star algorithm or so, if you don't tell it that actually when you're here, it's the same like being here, it starts searching and going somewhere, but it doesn't realize that you're actually here, right? So it's important. Now the interesting thing is, So now, let's say this was theta 1, right? So this is kind of representing the configuration space of theta 1 of the first joint angle. So now I have like, so now let's include the two angles. So like joint 1, joint 2. So what happens then? So for each of the theta 1, so you specify the first joint, so one value, like here. So, and then for each of these values, I mean for one particular theta 1, you get again like a circle for the second one. So what you can kind of pictorially say, you can imagine this like a circle here, right? For each of these points, you have this theta 2. And now if you do this for all the theta 1s, what you're getting is a torus, right? You get this donut. And that's why you should be careful by saying Rn. Because usually for all these regular jointed mechanisms, you have a torus. And they call it like Tn or something like this for the n-dimensional torus. It's like a donut. A donut is a two-dimensional thing. And then I don't know what this three-dimensional donut is, but you can imagine. Huh?
Sphere or something.
I don't know. Anyway, this is just, I mean, it might sound a bit far-fetched, but if you do motion planning, it's really important to consider this, right? Okay, good, there we go. Yes, so then, of course, surface generalized kind of coordinates. Right, so what we have to do, we have to look at twists. So that was, what we did here is the position, right? So we know, I mean, imagine here, we know the pose of our bodies in the kinematic chain, given the base motion, okay? But we are, of course, interested in the body-fixed twist, and, of course, in the twist of the complete system. So we should start by first saying, okay, the base, of course, is moving too. So we have a twist, I mean, the base has a twist, and it's, of course, VB, right? So just call it VB. And without mentioning it, we always use the body-fixed representation, right? But in the end, it wouldn't make a difference. Yeah, then we have the twist relative to the base body, because now the twist also of the body, I, for example, has first to be expressed in the base frame. And we have to have, of course, somehow a notation for this, and let's say we call it BI. Remember, this is like the position of the vector. It goes from 2, right? So it's from B to I, or the other way saying it's I relative to B, right? So body I and link I in our kinematic chain relative to the base, and the velocity is just this. And we know already how to compute the velocity. Right? We have the Jacobian. We have our Jacobian that we derived with these instantaneous co-coordinates, and then it's there. Anyway, no matter how you derive a Jacobian, it's there. You can do it in a different way if you like. Anyway, so this is there. So we know the velocity of the body I relative to the base frame. And then, of course, you know almost the velocity of the body I relative to the space fixed frame. And again, if you kind of followed the basic ideas, maybe not necessarily all this mathematics, you should understand what's written here. Again, because I kind of repeat myself, but it's good to repeat it. So VI, I mean the twist of body I relative to the space fixed frame. How do you get it? Well, first of all, it is depends where you start, of course. It's and I would like to represent it in the body fixed frame. Okay. So first of all, of course, it's the twist of body I relative to the base, plus of course the twist of the base relative to the space fixed frame. Pretty simple, I know. But you have to be careful, because the base twist, I mean the twist of the base, has to be transformed, I mean expressed in the body I frame. And that goes via this adjoint. And the adjoint gets HBI. Okay, what was HBI? So HBI was the pose of body I relative to the base, right? And remember that this adjoint, so when I said the pose, I mean this H was the homogeneous matrix, transforming from the I frame, body I frame, to the base, okay? So the inverse would be doing the opposite, right? It would be transforming from the base to the I frame. And then remember, the adjoint is the thing that does the same, but for screw coordinates. So the screw coordinates, I mean the twists, the twists are transformed by the adjoint of this guy. So it transforms twists from expressed in the base frame to those in the I-frame. So now we're transforming the base twist to the I-frame, and that's it. And then you can sum them up, okay? Otherwise you couldn't sum them up, you can just say this plus this. Okay, there we go. So I have an expression for the twist of body I, given the base motion twist, I mean the base is moving somehow, and the twist of body I. And of course remember, this is given by the Jacobian, so we can just plug this in and then we have a nice expression. And again, the overall system velocity is then again specified by what? By the base motion, by the base twist and the time derivative of the joint coordinates, right? Which is called the generalized coordinates. Yeah. So, what's the difference to the stationary kinematic chain? The difference is that now we have 6 more coordinates, right? So in the stationary system, we would have just Rn, we would have just theta dot. Okay. And now we have, because we have to account for the base motion, and maybe you don't see it.
Yes.
Okay. Good. Yes, and there is a bit of a non-holonomic geometry going on. Anyone knows non-holonomic kind of velocities and systems? A little bit. Not our topic, but I mean, essentially, it's about this twist here. We don't have to go into this. Anyway, so we have the velocity, okay? No. So, and what I said for the for body I, well, this equation, of course, has to be written for all the bodies. I mean, V1 up to Vn, okay? And then we are here. So V1 up to Vn, and I would like to express all the twists of all the bodies in the system. So all the bodies in the system, we have the base plus the end bodies of the link, of the kinematic chain. So the end bodies of the chain and then of the base. And this equation here, written for all bodies, we can do like this. So essentially what I'm saying is, we have the Jacobian times theta dot. And remember that we had this system Jacobian. So the system Jacobian, J times Q dot, just look at this one. So J times theta dot gives you the system twist vector. So it gives you all the 6 vectors of all the bodies, okay? And that's essentially what we have here as the first part. So this is actually this part for all the bodies. All right, so that guy times this gives you the first part of this equation. And then you need to then we have this contribution by the base twist. Okay, the base twist, this is this one here. So we have the adjoint of the transformation Bi. So B1, B2, B up to Bn. And I kind of collect them in a matrix, like a matrix, I call it U, and I call it U bar for some reason. And then we go. So essentially we have again, kind of a Jacobian that you multiply with the generalized speed that we said, because we said that our generalized velocities or generalized speeds are, again, theta dot and Vb, and that's kind of the compact form for writing the system twist, now comprising 7n twists, 7n components, in terms of the generalized velocities. Okay. Not much more to say. No, just have to digest it a bit, and everything is good. Good, yeah. More I cannot say. And of course, remember that we said we can actually factorize the Jacobian. And remember, I have to maybe stress this. That is the Jacobian that we already have. I mean, there's nothing else to do. This is the Jacobian of your stationary system, right? So you don't have to have a new Jacobian. It's the same Jacobian. So, and remember that this Jacobian we could split, right? We could factorize. We have been saying that this, for the stationary system, our Jacobian was J is equal to A times X. And that was, A was this triangular matrix, and X was this constant vector with its co-coordinates in it. And this is very nice. And exactly, as it says here. And we do the same, we can do the same for the Jacobian. I mean, it's JB now, defined in this way. JB is the one here. That gives you now the twist of the floating-based system, and we can do the same. We have a matrix A and a matrix X, but now they get a index B because they're a little bit different, but it's all the same. So we have again this factorization. Okay, yeah, we don't need this too much for us. I just left it in the slides. Now the motion equation, we get exactly the same way as we did yesterday, and that's the beauty about this kind of virtual power approach. Because what you do is, again, you just line up all the individual Newton-Euler equations. And remember that these equations are just the compact form, like all 6 equations, the compact form of the linear momentum and the angular momentum balance, which are the Newton-Euler equations. In the most general form, because we had them in a frame that is not necessarily attached in the center of mass. But you can do this, and then you have your good order Newton-Euler equations. And we do the same. The only difference is now that we have one more, right? So for the stationary, we just had the 1 up to n, to 1 up to n. Now we have one more. We have this base motion, right, which is there. Okay. And I hope you get a bit of this kind of the general idea about of this method, because first of all, you consider all these bodies, I mean, independently. You just say, okay, give me this body, and I write down the Newton-Euler equation. And then I'm imposing the kinematic constraint, so to say. I'm restricting it then. And if you do all this, and first of all, we should maybe this equation write it again in the compact form by saying that I can write this actually by saying I define again this matrix, the big matrix M, by just having the 6 times 6 mass matrices, the constant matrices on the diagonal. So essentially it's like this. And then of course if you multiply this, for example the first term, as we did yesterday for the stationary system, just we have one more matrix now. If you multiply this matrix, which is now a 7n times 7n matrix, with the time derivative of the system twist, you get exactly the first part of these equations, right? And then the same kind of the same game as we did yesterday. Then you have M, B, V, and pre-multiplied with V transpose, and V was this matrix that has the adjoints on the diagonal, okay? And then you get exactly this. So essentially what I'm saying is, this equation is a compact form of all these n+1 equations. Yeah, but I'm doing this because then I have a nice starting point for deriving the motion equations, in a sense that, again, from the principal variations, I impose the kinematic constraints, and what we have, of course, here is still the constraint ranges. Remember that we said we have, when we have the when we have the floating, I mean the independent bodies that are free floating independently of each other, then that's fine. But if we link them by joints or by other means, then of course we have constraint ranges. These are the forces that keep them together, right? These joint constraint forces and torques. And of course we have to include them here, right? So, and of course in this equation. The good thing with this principle of virtual power is that they drop out, and what is left is this equation. So you only have to, again, pre-multiply with the Jacobian transpose, and then you get eventually the motion equation. And if you do this, and if you introduce, of course, the term, which one? If you introduce this one, that one. So we know VB is JB times S, okay? It's always the same. Twist is Jacobian times speed. So you do introduce this here. Oops, you introduce this here in a sense that you have to, of course, substitute this VB dot and the VB here. Then you get exactly this equation. So the derivation is exactly as we did it yesterday. Okay, and then you get the mass matrix again. So you get a big mass matrix, of course. This is the first term, J transpose M times J, if you plug in the J times S for V. and then you get exactly the mass matrix. And again, the mass matrix is what we call a generalized mass matrix, right? So it has certain properties. Yeah, for example, it's symmetric. That's what you see hopefully immediately if you transpose the guy. If you transpose this, you get the same. Simply because the MB is symmetric and that goes from left to right. Yeah, and the rest is also the same. I mean, this looks exactly the same as the equation-heavy system, only that we have a B on index B, which indicates that we have one more component in the Jacobian. Okay? And there we go, and the gravity goes the same. Yeah, so I'm a bit fast because it's essentially the same, and you have to just look into the slides because otherwise you really need to just follow and look into detail this, but it's all the same. The gravity, as I was saying, goes the same, and there we go. Yeah. Okay, this essentially is what we have found for the motion equations I mean, these are the motion equations, the dynamic equations of motion, to be precise, for a floating-based system. Okay, what is the difference? The difference is that now our S, the generalized velocities, they have 6 more components because they have the base twist in it. And that's it. Right. And of course, in the generalized forces, we also have 6 more components, which is the wrench at the base. Okay, maybe we should look into a bit more into detail in the equations, because we started off, and this is the kind of basic difference here with the floating-based system. We started actually by saying that we have a base and a kinematic chain. And what you find when you multiply this, I mean, if you really, go there, because this JB, we have it all explicitly. If you have time and interest, just write it out. I mean, just this one. Go into and use this MB. So MB is just, that was actually, I mean, if you wouldn't have this MB, right, that was just the same as you had for the open kinematic chain. Right, and the Jacobian is almost the same as we had for the open kinematic chain, because the Jacobian is that for the stationary kinematic chain. But now we get one more kind of column here, right? So now just use it. I mean, this transpose times this M, this transpose times this M here, times J, and what you find is that this M partitions. It makes perfect sense, I hope so, right? Because it has to partition, because we have first the equation, I mean this part for the base, and then the remaining part for the kinematic chain. Yeah, and the same is of course for this the Coriolis term, I mean for this the C matrix, okay? And if you're really interested in, I mean you just compute maybe the C, and then you see that this is whatever it is. I mean, yeah. The thing is that everything again is actually easy to be implemented, because you just have to make this M matrix and the U matrix, and that's it. And then you multiply it. I mean, there's no rocket science behind it. There's a name for everything here, of course. That comes more from geometric mechanics, actually, respectively from space systems. Yes, that's right. That's right. How do I get you to this point? It might be interesting to try to understand what we have here. So the first, this MBB, or maybe we should again look at what we get actually. What do we get if you multiply this matrix with S? What do you get when you multiply this M with S? So again, S is not a speed, right? I mean, this is the generalized velocity of our system. Okay. As always, when you multiply this M with s, and s is now our speed, velocity. It's always the same concept. What do you get? A momentum, correct. So you get a momentum. Let's call this again P. Maybe B, because we have a floating based system. I'll just forget about it. Okay, so it's a momentum, correct. Now let's be a bit more precise, because you know exactly how M looks like, right? So it's MBB times MBC times MBC transpose MCC. Okay. I didn't actually say why I call it B and C. So the B stands for the base. So this is somehow related to the base. And the C is for the kinematic chain. C for chain. Now if you multiply this with what? With the base twist and our joint velocities, joint speeds. Then what do we get? We get MBB, I mean for the first part, we get MBB times VB plus MBC times theta dot, I guess, right? Okay, and then we get this part here, we get MCC theta dot plus MBC transposed VB. Okay, so that's what you get as a momentum here. Mm-hmm. And what you see, so when you say momentum, I mean, maybe conceptually it's important to understand how the splitting comes. Because maybe look at the dimension. What dimension, what is MBB? What is the dimension of MBB? Huh?
Mass is 6.
6. Exactly, it's a 6, because essentially it's this, I mean, if the kinematic chain wouldn't be here, that's just MB, right? It's just the mathematics of the base. So, but now the base, so yeah, exactly. And let's say let us assume that let's assume that this, that the chain, I mean the robot that is mounted on the base, is not moving. So it's locked. Say we lock the joints. Then this is 0, right? So essentially the momentum that you have at the base is, you know, as always, like, is MBB times VB. But the thing is, it's not, an important point now is, so, okay, let's say this. So we have the locked joints, okay? So locked joints means that theta dot is 0, okay? Then the first part of the momentum is MBB times VB, okay? Okay, but MBB is not just the mass matrix of the base. It is, what is it then? It's this guy here. It's this MB plus U transpose MU, okay? So this is the difference. So this is MB plus U transposed MU. And maybe it's good to understand what that means. Again, if the kinematic chain wouldn't be there, it's just MB, right? So it's just the momentum because of the inertia of the base itself. But now the base carries this, you know, kinematic chain. And somehow this must affect the inertia of the system. And that goes via this matrix here. Maybe we should look into this U matrix again. U's maybe here, so this one. So what does U do? Maybe look what happens if you, because what we do here is we multiply, oh yeah, I forgot VB of course. Yeah, so because what we do, we multiply U with VB first, with the base twist, right? So what happens if you, let me go over here, if you multiply U B with the base twist? Oh goodness. So we have the adjoint inverse of HB1 times VB. Okay? I'm just looking at this term, U times VB. And for the first component which is this one, right? The first component of U, you get this guy. What is it? Say again?
Velocity of base with respect to space time.
Represented in base plane actually. But a twist of the base represented in base
Spatial
plane.
It's the base twist, correct? What does HB1 do? HB1?
Transformation from the base.
Join to base.
Yeah. I mean, so HB1 itself transforms from 1 to B. I mean, from the link 1 to the base. So the inverse does from the base to the link 1. So now essentially this, what comes out here is the base twist transformed to the link 1.
And the link 1 is
The first,
link 1 is space plane here?
no, link 1 is just the first in our kinematic chain. So we have this, we have our robot here. So we the first link, the second link, and so on and so on. Okay? So we have the link 1 up to n. So this is it. And now maybe it's good to have this picture, because what we do now with this equation is we transform the base twist into the link. We started with 1, right? Into the first link 1. Other way, 1 is somewhere. Okay? So essentially, and what does it mean? It's like saying, okay, the whole kind of thing as a rigid body, that's why we locked it, right? Is moving. And you're measuring, because it's one big, rigid body. And we are moving, we are measuring actually the velocity. Okay, the whole thing is moving with a certain velocity, and we measure the velocity at the base frame. So the base velocity relative to the inertial frame is VB. And now I'm measuring this velocity at link number 1. So I know that link number 1, frame number 1 is now moving with a certain velocity because of the base motion. Okay? Not because of the joint motion, just because of the base motion. Okay? And of course you do, I did this now for 1. So this could be I if you want to. You can use it maybe if you like. You can write I in here. So you have MI, BI. So now we do multiply with M. Now it's, I know, it's a bit of too many M's here, right? M, and M is this one. This guy is M. This one. Okay, so I look at this M. So it's M1. So we multiply this with M1. Okay? Okay. Now I said I. What do you want? I or 1? Is I? I is good. Good. So we multiply this with MI. So what do you get? You get again the momentum of body I due to the motion of the base. Right? Okay, so this momentum is then multiplied with the transpose of that adjoint matrix. And it always, like, I said this at the first day or some, I don't know where. Because transpose inverse, because when you have a transformation and you take the transpose of it, it's always transforming wrenches or momenta, right? So essentially what it does, it takes the momentum that we just computed, which is the momentum of body I due to the motion of the base, and transforms it back to the base frame, right? So what you get here is actually the momentum measured at the base due to the motion of the base and due to the inertia of all the bodies, which is just a different way of saying, I have actually a big kinematic chain. All this thing is a big rigid body, and I'm accounting for the inertia of, maybe this way, and I'm accounting for the inertia of all these links, right? Because this is what I do. Transforming the velocity to the link, take the momentum here, transform it back, and I do this for all these links. So I have the total momentum of the of this system as a rigid system when I lock the joints, right? Due to the base motion. And this is why they call this MBB. Now come back to the notation. That's why they call this the locked inertia matrix of the system. And it's an important object. So let's say you have humanoids, I mean floating-based systems, right? So you are interested in what is the kind of inertia that the whole system is just having if you're kind of moving the base. If you are actuating the base, for example, right? And not actuating the joints. The joints are locked. But what is then the inertia that you have due to the I mean, what's the inertia that you're kind of measuring at the base at the current configuration of your system? When I'm saying current configuration of the system, I'm not sure if I have a picture here or what. So, no. Okay, the picture goes here. Because of course, the momentum that you get, so to say, this locked inertia, or let's say the inertia properties that you're measuring, and if you can, I mean, kind of virtually consider you grasp the system, you kind of take the base frame, and you would like to move it around. What kind of inertia do you feel? And of course, this inertia depends on the configuration of the arm, right? And that's why it's important, because it tells you that at a certain configuration of the arm, you have such and such an inertia. And you can imagine that, of course, if the arm, for example, is folded, then the inertia becomes a bit smaller and so on, because it's not just a big thing, it's just a small one. And that's important for many applications. And there's also, when you are in humanoid, for example, humanoid motion planning and so on, has to do with this, what's the name? Inertia ellipse. Oh, no, I forgot it. Who's in humanoids? The term is, I'll think about it, I should remember. Anyway, you can imagine that this is of course important, right? Because when you have your humanoid, walking robot, then you are interested in the inertia relative to the hip or so, right? Or to the foot or so.
Inverted pendulum?
No, this is a model actually that you mentioned. But anyway, yeah, it's not the point. Anyway, so for it's obvious, I guess, that it's important. Yeah, okay, and this is, yeah, so this was the term, or let's say terminology that we used it, the locked inertia. And now we have this other thing that more comes from space systems, because what about this part here? Now what you can say now, for example, I mean, you can always look at extremes, right? One extreme is that now the base is not moving, right? So let's say the base is fixed. So then VB is 0, and the momentum that you measure at the base, right, is only due to the motion of the kinematic chain, theta dot. And that's exactly this. So theta dot is multiplied with MVC, and MVC is this part here. And we could try to understand it in the same way, because what does maybe we should write it out. So MVC, now it's a bit getting full here, MVC theta dot, and MVC is that one. It's U transpose M. J times theta dot. Okay, now it should be clear actually, because J times theta dot, exactly, is the system twist. U transpose MV, right? And now it's the, but remember, this is the system twist, right? So again, you have this M1, because here we have the again the inertia of the first body, second, and so on. All the bodies in the link, in all the links or the bodies in the kinematic chain, multiplied with their twist. And now the twist is due to the motion of the kinematic chain, because we move the joints. And then the argument here is the same. You transform and then you get a momentum, of course, right? Because you multiply M1 with V1, M2 with V2, which is in a system twist. And then you transform whatever you get, you transform it back. The same argument here with this U transpose, because U transpose gives you this part, back to the base. So essentially what you get is the momentum at the base due to the motion of the kinematic chain. Why could this be? Oh yeah, so first of all that's it, and that's what I call the coupling, inertia coupling matrix. Anyway, but why could this be interesting? I mean, let alone floating-based system. Why could this be interesting for someone that works in industrial robotics? Again, what you're getting is the momentum at the base, which has to do with the wrench at the base, the force and the torques, due to the motion of the kinematic chain. So essentially what you're getting here is the effect, I mean, let's say the load at the base, right? The load at the base, let's say on the foundation. So you have your robot, you mount it somewhere, and you're certainly somehow interested in what force and torque do I actually need to hold the system when I do motions, right? So when I do perform certain velocities and accelerations. And that's what you're getting out of this. Yeah, okay. What else did I try to do? Yeah, and in the end, I mean, you can write them explicitly because you can multiply this all with this S and B and so on. And in the end, what you're getting is a system of, two coupled systems of equations. So the first one apparently has to do with the base, and the second one with the kinematic chain. And here you get exact, yeah?
How do we calculate inertia coupling matrix numerically?
Oh, so the question was, how do I compute this matrix? It's very simple. You just evaluate this. I mean, these are the symbolic expression, and you just plug in numbers if you want to have it numerically. So all I'm showing hopefully makes sense in for implementations, because I mean this is the basic idea, because all this stuff is easy to implement. Yeah. Remember, I know it's a lot to take in for one week. What is it then? I mean, you know homogeneous matrices, right? So this is this. The adjoint is just a 6-6 matrix that you construct from the homogeneous matrix. So this is a 6-6 matrix that you can compute. And so on and so on. I mean, the matrices you have to find, because this is what you get from your inertial properties of the bodies, and then you have it all. And then eventually, I mean, this is a good point actually. You can do this symbolically, which is a good idea, because then you have a symbolic analytic expression and you can plug in numbers in whenever you like them. But you can of course also say that you're always working with numbers. I mean, in a sense that you always have the specific, concrete, particular, metrics when I have a certain pose. I mean, what I'm saying is like you have 6-6 matrices just with numerical values. That's also what you can do. It depends what you want. Or it depends it depends what's more efficient. And usually it's more efficient to have this analytically. Okay, I'm not sure if we should stop.
Yes.
Okay, then let's have a break.